Hello, dear viewers. The concept of fractal temporal dimensions suggests a profound shift from classical to quantum time structures, framing time not as a single linear trajectory, but as a dense, multidimensional continuum. This fractal temporal dimension manifests itself as an additional thickness in time, labeled by the orthogonal axes ET prime and T double prime, and illustrates the fractal nature of time as a dynamic, space-like structure. This temporal thickness can encode spatial properties, potentially creating a fractal structure that fills a plane as temporal intervals become thinner. For full articulation, it also requires an additional spatial dimension. This brings an analogy to special relativity, where time and space are intertwined to form spacetime, with each additional component giving rise to an interdependent structure governed by the metric tensor. This statement suggests a relationship between spatial and temporal intervals and suggests that time can take on spatial-like qualities under certain conditions. The classical, one-dimensional view of time expresses a fractal thickening of time, transforming into a two-dimensional fractal form. This fractal form implies a shift from linear temporality to a dense, spatial-like continuum, with the temporal thickness becoming more apparent as we explore smaller and smaller scales. In this regime, time acquires a spatial coherence that points to a new space-time structure that is fundamentally different from both the classical and relativistic frameworks. In considering this additional temporal dimension, it is important to consider whether a prime and T double prime are truly spatial or merely components of a new, timeless field. Here, the idea of a timeless dimension as an addition to the temporal structure is compelling, especially when we consider the quantum state operating in a coherent, non-local manner. Coherence and delocalization in the quantum realm contrast sharply with the classical, localized framework. These qualities differ from the classical tendency toward disorder. This coherence implies that the quantum realm maintains a uniformity of phase relationships over large distances and times, unlike classical systems where chaotic interactions dominate. To understand this coherence, consider the wave functions of quantum mechanics, where coherent states imply a constant phase difference, preserving the collective behavior of particles. This coherence is metaphorically like two oscillations moving in perfect synchrony. The coherence decreases as they become out of synchrony, paralleling the increasing disorder that classical systems typically exhibit. Thus, quantum coherence here is not just a local property, but an intrinsic global property. The concept of delocalization is equally important. In classical systems, objects maintain fixed positions and obey spatial constraints limited by causality and the speed of light. However, in quantum mechanics, delocalization refers to the absence of fixed locations, where particles exist in superpositions that extend across space and allow for instantaneous correlations. Delocalization implies that spatial separation no longer governs interactions. Particles or quantum states are interconnected and not constrained by locality. This property underlies phenomena such as quantum entanglement, in which distant particles exhibit correlations that defy classical explanations. Photons traverse conventional space-time during their light-speed travels, experiencing no time or space themselves, thus living in a timeless or extra-dimensional perspective. In a timeless realm, the concept of location breaks down as photons, immune to space-time constraints, can interact with distant points non-locally and communicate without traversing the intervening space. This property is closely related to the Einstein-Podolsky-Rosen EPR paradox, in which entangled particles such as photons exhibit instantaneous correlations despite spatial separation. From the perspective of timelessness, the position of the photon does not exist, allowing it to embody a fundamental coherence between space-time points. This concept extends to the provocative hypothesis that all photons may be manifestations of a single entity that appears at various points throughout spacetime due to their interactions with other entities. Such a hypothesis is compatible with the concept of a unified quantum field, in which individual particles are not separate, but rather expressions of an underlying, coherent field. In this timeless and non-local coherence, all photons are fundamentally one. But from our space-time-bound perspective, they manifest as separate, localized particles. This unity of identity in the relativistic realm emphasizes the non-locality inherent in the timelessness of the photon. The transition between the classical and quantum worlds is characterized by a fractal process known as the Wiener process, which describes random or Brownian motion. In the context of quantum mechanics, the Wiener process models probabilistic particle paths and grounds the transition from deterministic classical trajectories to probabilistic quantum paths. However, as time is infinitely divided into fractal dimensions, these paths evolve with fractal-like density, potentially forming the basis for a deterministic chaotic transition from quantum coherence to classical incoherence. Fractal space-time theory synthesizes these concepts while offering a unique lens through which to view the coherence and non-locality of the quantum realm. The thickened temporal dimension can serve as a bridge that reframes classical and quantum relationships and suggests an inherent fractal structure of time itself. While classical physics adheres to local, deterministic laws, quantum mechanics operates on a consistent, probabilistic basis and frequently defies locality. The presentation of the Wiener process as a reversible process becomes important in understanding this transition. The Wiener process connects quantum coherence and classical decoherence through a fractal-like mechanism. As it loses its locality, coherence emerges. As it decoheres, relocalization occurs, and the quantum classical boundary is established. The Wiener process, used in both classical and quantum transitions, has historical roots in describing stochastic, Brownian motion. Yet here it takes on a more fundamental role as an interface between the two regimes of reality. Bohm's concept of implicit and explicit orders and Whitehead's concept of unification describe the unfolding of potentials into distinct states in a way analogous to the collapse of quantum superpositions into distinct classical results. The fractal model implies that fractal time structures inherently support a reversible interaction between quantum superpositions and classical manifestations, and suggests that the Wiener process involves a fractal progression in which quantum probability densities are transformed into classical, localized certainties. Fractals, by their iterative nature, provide an apt metaphor for this transition. Through repeated iterations, a simple mathematical function produces a complex structure, as seen in natural formations such as mountain ranges. Similarly, the latent potentials of the quantum realm are iteratively refined through the fractal structure of time and crystallized into observable phenomena of the classical realm. This formulation captures both aspects of this process and suggests that the transition is not one way. Just as wave functions collapse in measurement, they can also reform under conditions that allow quantum coherence, thus allowing reversible dynamics. The statistical nature of the quantum realm generally allows for symmetry in time, where particle trajectories are theoretically reversible. The implication is profound. Time itself seems to be shifting from a bidirectional, fractal symmetry in the quantum realm to the unidirectional flow we perceive in the classical realm. This model of integral time proposes a coherent framework in which the various manifestations of time are integrated into a structured whole, reconciling microscopic reversibility with macroscopic irreversibility. For example, particles and their antiparticles, particles moving backward in time, coexist in equilibrium on quantum scales. and as time thickens into its classical dimension, the apparent imbalance between particles and antiparticles emerges, reflecting a temporal asymmetry. Photons, on the other hand, exemplify an idealized symmetry between past and future, operating beyond the constraints of temporal locality. By framing the quantum classical interface as a fractal structure, it reconciles coherence and locality, reversibility and irreversibility, and offers a coherent view of time that integrates both timeless and time-bound states. This model proposes that temporal dimensionality is scale-dependent, fractal at the quantum level, and linear at the classical level, offering a unified perspective on the nature of time. This is a fundamental continuum that provides coherence between the hidden and manifest realms. The discovery of the fractal dimension of time has challenged classical interpretations by suggesting that time, in certain quantum non-relativistic scenarios, exhibits properties similar to fractal dust, with a dimension smaller than 1. Here, the fractal structure appears not as a continuous line or surface, but as a dust of points that lacks continuity and is characterized by infinitesimal, isolated moments. This perspective leads to the idea that under certain conditions, time behaves not as a continuous flow, but as a set of discrete, scattered instances, much like a Cantor set, where successive slices produce a structure of points without length or measurable continuity. This topological dimension of zero resonates with our subjective experience of time, as moments appear fleeting, ubiquitous, yet eluding our grasp, reflecting the paradoxical nature of time. In quantum mechanics, where time behaves fractally, this fractal dust structure suggests that time can appear as a collection of infinitesimal moments without a coherent expansion. Such behavior contrasts sharply with time in relativistic quantum scenarios, which assume two fractal dimensions and propose a fuller, thicker temporal structure that can be attributed to higher quantum coherence. The conservation of energy depends on the uniformity of time. If time is not uniformly continuous, but rather quantized or fractally distributed, then energy can also be quantized, offering a new perspective on the quantum classical transition. Using the Koch snowflake as an analogy, Susie Vrobel introduces fractal measures such as levels of description LODs, temporal depth, temporal length, rate of condensation, and temporal density, and aims to bridge the gap between the fluidity of time and fractal mathematics and our experience. LOD describes the scale at which time is measured, with finer scales capturing greater detail and irregularity. The choice of LOD affects not only temporal measurements, but also our perception of duration and temporal richness. Temporal depth, represented by the number of self-similar levels within a fractal structure, refers to the number of scales, or levels of organization that time spans. The greater stratification of the fractal structure of time is reminiscent of the fact that we can experience time as a hierarchy of nested intervals, such as years, days, and seconds, each encompassing finer detail. Temporal length measures fractal length at a single level of description, emphasizing that, unlike classical measurements, fractal time lacks a fixed unit and instead depends on the scale chosen. For example, on the Koch curve, the length of the line increases exponentially as the scale becomes finer. Similarly, temporal length contracts as each successive scale represents a progressively finer portion of the initial interval, illustrating how the apparent duration of time can fluctuate depending on the fractal scale. This is the rate at which one LOD contracts relative to another, representing the rate at which temporal length changes with depth. In fractal terms, this corresponds to the scaling factor between successive levels. In the Koch snowflake, for example, each level is 3 times finer than the previous one, capturing the acceleration or deceleration of time across scales. Vrobel's rate of condensation therefore reflects the experience of time moving faster or slower, depending on context and scale of observation. Temporal density, equivalent to the fractal dimension, quantifies the density of temporal intervals at each level. This density refers to the richness of events or experiences embedded within a given temporal interval, and coincides with our perception that certain moments feel intense and significant, while others feel sparse or mundane. The fractal model thus accommodates both the timeless and the temporal, allowing for a richer interpretation of how we experience the flow, density, and variability of time. Our experiences of remembering, thinking, and learning deepen the structure of time by adding levels of description, LODs, or layers of perception and memory. This subjective layering effectively increases temporal depth and density, enriching the experience and changing our perception of the flow of time. For example, when revisiting shared memories, individuals may find that time flies because of the wealth of LODs, memories and associations, activated during the event. In contrast, a stranger without these memories processes fewer LODs, making the event feel longer and more monotonous. Thus, the subjective richness of the experience narrows the temporal length and accelerates the apparent passage of time. As temporal depth increases with more LODs, time is fragmented into finer pieces, allowing for the complex layering of memories and information. The model suggests that the full time of rich experiences creates a rapid flow, while the empty time of sparse experiences stretches. This perspective is consistent with temporal density. When experiences are rich with detail and connections, they feel more significant and memorable. If an experience lacks density, it remains shallow and can fade into oblivion unless subsequent thought embeds it in new LODs and strengthens its presence in memory. According to Penrose, insight is the ability to grasp a pattern or concept instantly, a reflection of understanding that seems to originate in a timeless realm. Frobel suggests that insight is like moving away from fractal time to perceive a pattern in its entirety in a single moment. This contrasts with the zooming in or condensation that occurs when memories or information are processed and time is deepened through recall. While condensation corresponds to the forward flow of time as we build structure through experience and memory, insight, zooming out, can reflect a reverse or timeless perspective. This dynamic between condensation and insight highlights the dual nature of time in human cognition, the layering of experiences on the one hand, and the ability to achieve whole understanding in moments of clarity on the other. At the heart of the model is the concept of the fractal prime, the smallest indivisible unit of a fractal structure, beyond which further subdivision is impossible. The timelessness of the prime means that it exists outside the conventional flow of time, facilitating instant insight. In fractal time, the prime serves as the foundation for larger, self-similar structures, embodying the underlying pattern upon which other temporal layers are built. This concept of the timeless prime can be extended to the photon, a particle that has no temporal scale and exhibits timeless properties. If the photon is considered the prime of a universal fractal, then the whole of reality can be understood as a fractal extension from this fundamental, indivisible entity. The wave-particle duality of the photon reflects the scale-invariant nature of the fractal and suggests that this duality may constitute a fundamental pattern at all levels of reality, as described in the Schrödinger equation. Penrose argues that insight's access to timelessness is a non-computational process potentially linked to the self-collapse of the wave function, a quantum phenomenon that can bridge time and timelessness. Notal develops this concept by saying that particle trajectories follow fractal geodesics, with each path representing one of an infinite number of possible quantum trajectories. The wave function thus represents a family of these geodesic paths, embedding nonlocal, timeless information within the structure of the particle itself. Below the de Broglie wavelength, time transitions from a linear to a two-dimensional fractal structure, adding a second dimension that can be seen as timelessness. While Vroebel's timeless prime emphasizes the smallest, indivisible unit, Natal's approach assumes fractal structure to be a continuous property up to an upper limit that is only valid at quantum scales. To reconcile these views, we can think of timelessness as an intrinsic aspect of fractal patterns at any scale, something that is not limited by an upper or lower limit. Timelessness would then exist not merely as a boundary condition, but as a fundamental feature of the fractal process. In this synthesis, timelessness is both the pattern and the container of fractal time, appearing at each level of iteration within the fractal structure. Rather than existing only at an indivisible boundary, as in Vroebel's prime, or at a superquantum threshold, as in Nonlocality's fractal spacetime, timelessness can represent the continuity of the fractal pattern at all scales. This perspective resolves the boundary conflict and proposes timelessness as the underlying constant of fractal time, a concept woven into both the subjective and objective structures of experience and reality. Natal's notion that fractals are more fundamental than differentiable structures reflects this. Fractals, such as the Mandelbrot set, are characterized by infinite complexity and lack a lower limiting prime, making them candidates for these fundamental patterns that structure the universe. In this context, consciousness engages in the fractal process of compressing and organizing data into memory, enabling the identification of such primes. This process involves stepping outside of data, a function of the mind, which allows one to observe and recognize patterns across experiences, as if from an external perspective. Stepping outside of data is, in essence, a step outside of time. Every time we condense temporal experience into memory, we bring a moment from the past into the present, creating a synthesis between time and timelessness. By viewing data gathered over time in a single moment, consciousness produces a timeless perspective that reveals the underlying pattern in a condensed form. This timeless perspective also applies when we predict the future by considering possible outcomes based on past patterns. Through predictions, we bring the future into the present momentarily, creating a timeless moment where the past and future intersect. This moment of synthesis, where possibilities from the past and future merge into the present, can be seen as the self-condensation of time, a process that emerges from the interaction of temporal experiences and timeless insight. The concept of two horizons, one external, one internal, further clarifies this dynamic. The external horizon is the immediate boundary of our present experience, encompassing everything we perceive and remember. The internal horizon consists of condensed memories that accumulate with age, expanding one's knowledge while also potentially reducing memory resolution due to the volume and layering of data. This trade-off reflects a fundamental feature of the fractal model of time. A larger internal horizon supports greater insight because it contains more patterns and LODs, but at the potential cost of resolution and clarity. While subjective time corresponds to McTaggart's A series, which is based on the changing present of the perceiving subject. Objective time is compatible with the B series, which is marked by static, relational, earlier-later distinctions. Objective time is positioned as primary, serving as a stable framework within which subjective time is layered. We experience objective time only through the subjective lens. Therefore, it may be more accurate to think of subjective experience as equally fundamental to our understanding of time. The concept of primacy itself may be limited when applied to time, since the concept is inherently tied to temporal relations. McTaggart's solution involves a non-temporal C series, encompassing both the A and B series, viewing time as an illusion against a timeless background. While McTaggart interprets this timelessness as a denial of the reality of time, Froebel and Nautilet's perspectives suggest an integrative model in which timelessness and time coexist in a fractal structure. This approach redefines time not as an illusion, but as a subset of a more complex, multi-layered temporal reality in which timeless patterns coexist with directional flows. Froebel's model suggests that timelessness and temporal processes are intricately linked through the fractal structure of experience and memory. This interplay between condensation and insight parallels the flow of time. Condensation, or zooming in, reflects the forward progression of time as we accumulate experiences, while insight, or zooming out, can represent a reversal or momentary transcendence of the linearity of time, allowing one to perceive patterns from a timeless perspective. Rather than timelessness being limited by a boundary, it can represent the inherent scale covariance of the fractal. Its coherence across all scales serves as the foundation, pattern, and container of time itself. This view overlaps with Nautilet's fractal spacetime, which proposes that time exhibits fractal properties up to a certain scale, and suggests that timelessness permeates reality as a scale, invariant aspect of fractal patterns. The concept of temporal density illuminates the paradox of how we perceive time differently, depending on the density of information within an experience. For example, a mundane or boring experience, while seemingly endless at the moment, becomes dense in memory due to the lack of meaningful stimuli and becomes almost insignificant in retrospect. Conversely, an exciting experience, although fleeting in its experience, retains an intense and extended presence in memory because of its richness and multiplicity of layers. This phenomenon is consistent with John McCrone's observation that our memories tend to compress sparse, uneventful intervals and magnify time-rich, stimulating events. To contextualize this phenomenon, Froebel proposes three separate measures of time: experienced time, the time perceived during the event; retrospective time, how long the event seems when thought about; and clock time, the objective duration measured by a clock. Temporal density, therefore, reflects the ratio of content to clock time and summarizes how our minds fill time with different levels of information and layers of experience. The more information or stimuli in an interval, the more intense the experience, leading to the perception that time flies in the moment but stretches in memory. If time progression is indeed a fractal deepening as suggested, then each time interval, second, minute, year, can be viewed as a step in scale. The fractal model implies that at each successive scale, there is an exponential growth in data, or temporal density, and a linear increase in time. In other words, each level of scale, or temporal step, brings an increase in condensed information. This process is consistent with the idea of logarithmic scaling in fractals, where each decrease in scale deepens the fractal structure and reveals more detail within the same spatial or temporal interval. This fractal time density serves as a model for understanding how subjective time expands or contracts, depending on the intensity of experiences within a given hourly interval. The logarithmic nature of fractal scaling translates into a temporal experience. The deeper the scale, or the more information it contains, the more time one subjectively feels in that interval. Froebel calls this process the speed of condensation, the speed at which time condenses experiences into layered, timeless memories that help form subsequent moments. The speed of condensation thus connects the timeless beginning to the experience of emergent temporal events, where each moment contains the potential to condense experiences, layer memories, and project them onto future moments. But this fractal deepening does not lead to an infinite subdivision without progression, as Zeno's paradox might suggest. Rather, each moment serves as a separate dividing point, a fractal structure in which the past, present and future are intertwined. Each step in the scale creates both depth and continuity, embedding previous moments into each present instance as it advances time. In this model, each fractal level corresponds to a layer of memory or data from past moments, creating temporal depth. This depth, in turn, allows each new moment to integrate previous experiences into a unified pattern. Over time, these layers expand the horizon of knowledge in the mind, allowing insights and patterns to emerge from the accumulated data. However, as depth increases, the details in each layer can become less clear. This is a compromise between insight and the clarity of individual memories. Frobel aligns subjective measurements of time, how long an experience feels, with temporal length, suggesting that this is a function of subjective perception rather than an objective interval. Temporal depth, or the layered structure of moments, increases linearly as each new moment is embedded in the previous one, creating a subjective experience of continuous time. But this deepening also has implications for objective time, as it implies that the temporal depth of each moment may be a fundamental aspect of how time objectively unfolds. By arguing that temporal depth and linear time are equivalent, Frobel proposes a model in which subjective time, the experience of instantaneous length, reflects an underlying fractal structure within which both consciousness and memory interact. Extending Frobel's model, it can be argued that wave function collapse represents a more fundamental level of temporal depth, even in the absence of conscious perception. In this view, memory is a complex manifestation of the process of collapse, condensing experience into layers that create temporal depth. Thus, the fractal structure of time not only models subjective experiences, but can also describe the objective emergence of time from a timeless state, with subjective time representing one layer within this larger fractal temporal framework. By treating time as a fractal structure, Frobel and Nautili's theories converge into a model in which each moment is both an autonomous unit of progression and an intertwined element within a larger temporal structure. Temporal density, experienced differently according to the richness of stimuli and memories associated with each moment, aligns subjective and objective time within a unified fractal model. Each new moment inherits and builds upon previous moments, condensing past knowledge and expanding the horizon of knowledge in an iterative process that blends time with timelessness. In this model, subjective and objective time are complementary, not opposite, aspects of a fractal structure. Temporal density, or fractal dimension, reflects the extent to which a moment is filled with content and influences how it is experienced in real time and how it is remembered retrospectively. This integrated approach suggests that timelessness is not merely an endpoint or boundary, but a fundamental feature of fractal time itself, supporting both linear and nonlinear aspects of temporal experience and providing continuity within the progression of time. Thanks for listening and take care.